This video will look at examples of solving polynomials using various methods. So number one, we have the polynomial f of x equals x cubed minus 27. We look at this and we'll notice that we have a difference of 2 cubes. So to solve this, let's factor this down using our formula for the difference of 2 cubes. And in order to do that, we have to identify our a and our b. So remember, our general form for the difference of 2 cubes is some perfect cube minus another perfect cube. So identifying the a value is going to be taking this cube root of the first term, which would be x, and the cube root of the second term, which would be 3. Again, we don't have to interpret the b as negative 3 because the fact that we're identifying it as a difference of cubes and using the correct formula to factor it will take care of the signs for us. So the factorization, x cubed minus 27, is equivalent to, it's going to be a, and then, sorry, I'll just put the actual a value, which is x, and then the first sign is same. So we're going to use that SOAP acronym, same. So a minus b. Actually, why don't I just write what the actual formula is. This is for the difference of cubes, so you'll see same, opposite, always positive in terms of the 3 signs of the factorization. So if we're looking at x cubed minus 27, the equivalent, we've already identified a and b. A squared is x squared, plus 3 times x is 3x, which would be a times b, and then plus b squared, which is 9. So we have the factorization. Our ultimate goal is to figure out when this equals 0. So this factorization has allowed us to take that difference and rewrite it as a product of 2 things. Using the zero product property, for this expression to equal 0, one or both of these 2 pieces needs to equal 0. So we're going to consider the possibility that either could be. So we set each one equal to 0. The first one is easy to solve, and we'll get our first solution, x equals 3. The second one is a quadratic. To solve that quadratic, we have various methods. Unfortunately, it cannot be factored, so we'll have to use quadratic formula. So let's jump back so I have enough space. We already know one of our solutions is x equals 3. To find our other 2, based on the fundamental theorem of algebra, I know I should have 3 complex solutions in total. We're going to get our other 2 from this quadratic. So let's identify a, b, and c. So a is 1, b is 3, c is 9. Quadratic formula, x equals negative b plus or minus b squared minus 4ac all over 2 times a. So x equals negative 3 plus or minus. We're going to have 9 minus 36, which is negative 25. No, sorry, negative 27 over 2. Let's clean this up. Take out an I. 27, that square root can be simplified, right? This is the same thing as 9 times 3, root 9 times root 3, 3 root 3. So we're going to have x equals negative 3 plus or minus 3i root 3 over 2. So that's what we'll get for the first solution pairings for number 1. So here, again, in a fully simplified format, our 2 solutions, because of the plus minus and the 3, we found all 3 complex solutions that we were looking for, and we found them using the difference of cubes factorization, breaking that up and solving each piece. And we're going to look at number 2. Okay, so we have a quartic. We expect 4 complex solutions. What I might do to start is, because I'm going to notice this 27, this 8 are perfect cubes. We have a plus in between, but the x to the 4th and the x aren't. However, we can see that because they share an x, those two terms, we can factor that out. And what's left over is a sum of cubes. So the factorization of the GCF, and again, we want to find the zero, so we want to know when this equals 0. Let's take this sum of cubes and factor that further. So let's identify our a. Our a is going to be the cube root of the first term, which is 3x. b is the cube root of the second term, which is 2. The factorization for a sum of cubes. Same structure as the difference that we saw in number 1. So the only difference is that the signs are a little different. So it's going to be same, opposite, always positive. So now it's just a matter of plugging in. So to get this factorization, our a, write it off over here. We had 3x plus 2, a squared, so 3x squared is 9x squared, minus a times b minus 6x plus 4. Okay, so this is a fully factored form of the original polynomial we started with. We have 3 pieces being multiplied together. So we took a sum of 2 terms and rewrote it as a product of 3 things. If those 3 things are multiplied together and they equal 0, zero product property tells us one or all or 2 of those things has to be 0. We're going to take that into consideration by setting each piece equal to 0 and solving each one to find our solutions to the original polynomial. The first 2 are just linear equations. This one's already solved for us. This, subtract 2, divide by 3, we'll get negative 2/3. We've already found 2 of the 4. How do we get the remaining 2? We have to solve this quadratic. This quadratic cannot be factored, so we're going to use quadratic formula, or you could do completing the square, but I don't want to do that. I don't want to deal with the fractions. So a 9, b negative 6, c is 4, so x equals negative b plus or minus b squared minus 4 times a times c, all over 2 times a. So we're going to get 6 plus or minus, we're going to have 36, and 16 times 9 is 144. 36 minus 144, go to the calculator here real quick, negative 108 all over 18. We have a negative under the square root. Let's remove that. We'll have that I there, so we have an imaginary solution here. Square root of 108, we can break that down. I'll do it all the way over here to the left. We have 2 and 54, 2 and 27, 3 and 9, 3 and 3. So we have 2 pairings here. So 3 times 2 is 6. Root 3 is the equivalent. So let's make that replacement by saying that this equals 6 plus or minus 6i square root of 3 over 18. Now, the 6's and the 18 are all divisible by 6, so let's do that. So 1 plus or minus I square root of 3 over 3. There are 2 solutions there. Again, we have 1 plus I root 3 over 3 and 1 minus I root 3 over 3. Oh, 3. So we have 4 solutions. 1, 2, 3, 4. This was a quartic. And again, another example of solving a quartic by factoring the sum or difference of cubes. And after I factor that thing fully, it also required a GCF in this problem. When you do a sum or difference of cubes, don't forget that you can solve this quadratic. Unfortunately, it's not going to be factorable, so you're going to have to use quadratic formula or completing the square to get that solution, but we've already gone over that in class, so you can handle that. You'll have that linear piece from the initial factorization, so take that into account, or maybe it's not linear, but we'll keep it linear for now. And if you have a GCF, don't forget that this GCF is still there, and that's going to give you a solution too in some cases. So there are all 4 solutions to that one. Let's jump down to 3 and 4 and look at some other methods we can use to solve polynomials. For number 3, we have 4 terms here. And what we'll notice is that 2 to 10 is times 5, and 5 to 25 is times 5 in a rough sense. I mean, -5 and -5, whatever, but they're 5 times larger. So that's a good indication we have a grouping problem here. We can see that scalar going on. So let's try to group these things. Let's group this as our first group. Let's establish these 2 groups. We're going to take a GCF out of that first group, which would be 2x cubed. We're going to be left with x minus 5. And if I remove a negative 5x from that other group, we'll have x minus 5 as well. So the fact that I was able to remove things from those 2 groups and be left with the same term here tells me that this grouping was possible. Now, we didn't establish new groups, but rather we just reformatted the 2 groups we were looking at originally. And when we reformatted, what that revealed to us was that now these 2 groups share the GCF of x minus 5. Not necessarily GCF, I should just say they share the common factor of x minus 5. So I can remove that from these 2 groups. I have 2x cubed minus 5x. Remember, we're trying to find the zeros here. So let's set these things equal to 0. We have x minus 5 equals 0. X equals 5. There's one solution. How many are we looking for? We're looking for 4. So let's look at that other piece, 2x cubed minus 5x. How are we going to solve this? Well, let's take a GCF out of that. We'll have a 2x squared minus 5. So we can break this up now. We have x equals 0 from that GCF. Then we have 2x squared minus 5 equals 0. This is a quadratic that does not have a linear term. So we can just solve directly for x. And we're going to get x squared equals 5/2. Take the square root of both sides. And don't forget the plus or minus. Now, you might see this rationalized, but I will let you keep it in this form for now. But if you're interested, you're not technically supposed to have a square root in the denominator in formatting. So to get rid of it, we can break this up. And we can rationalize the denominator, which what we're going to do is multiply the top and bottom by the square root of 2. So technically all we're doing here is multiplying by a form of 1. And multiplying by 1 doesn't change the value of what we started with, but rather it can just change the way it looks, which is what all we're trying to do. We're trying to get that square root out of the bottom. And the reason we've chosen these values is we're going to leverage our square root properties. Because root 2 times root 2 is root 4, which is 2. And root 5 times root 2 is root 10. So square root of 10 over 2 is the same thing as square root of 5/2. And now I've gotten rid of the square in the denominator. But if you left your answer like this, no big deal for now, because the main focus of this video is can you just reach the solutions using various methods. So we were looking for 4 complex solutions. Did we get all 4? We have plus minus square root of 10 over 2. That's 2 of them. 5, 0. There's our other 2 for a total of 4. So that's using grouping to find solutions to the polynomial. Number 4 will also be a grouping problem. You can see that the scale from the first number to the second number is times 1.5. And from this value to this value is also times 1.5. So there's a good indication that grouping can be used. So let's establish the 2 groups. Let's take out a GCF in the first group. We'll have the 2x minus 3. We got to take out a 5 from the second group. Again, we didn't establish groups, but rather just reformatted their appearance. Now both of these groups share a 2x minus 3, so let's remove that. What's left behind is the x squared plus 5. We want to know what the zeros of this polynomial are, so let's solve this. We have a product of 2 things equaling 0. Using zero product property, we'll set each piece equal to 0 and solve each one. Linear, so we're just going to get x equals 3/2. There's one solution. And then for the other one, we have a quadratic with no linear term, so let's just solve directly for x. We're going to get x squared equals -5. X equals plus or minus the square root of -5. So again, don't forget those plus minuses when we're using that square root property. And a negative square root, we're going to say this is plus or minus I root 5. We would then look to simplify the square root of 5, but it cannot be. So here are two more solutions, two imaginary solutions. So a total of 3 have been found, and we're done. So there's using grouping, or another example of using grouping to find solutions. Let's go over to 5 and 6. So this is going to be basic factoring here. So we're not going to be able to group with the terms we have, but let's look to take out a GCF. So, or actually, rather than writing f of x, we take out an x. Now, that might be my initial move, because what I would see is that if I remove an x, all I'm left with is a quadratic, and we spent a great deal of time on solving quadratics. So if I want to find these zeros, removing that x initially, I can find the 0 for this GCF, so I have a product of two things again, equaling 0. So I know x equals 0 is one of my solutions. I'm going to get the other two from this quadratic. Now, let's try to factor this thing. So because we have an a value greater than 1, we're going to have to do that split the middle. So we're going to do a times c is equal to -36. What multiplies to -36 but adds to +5? And with some thought, we'll get 9 and -4. So that's how we're going to split the middle. So let's say 3x squared plus 9x minus 4x minus 12. Now we have a grouping scenario. So let's take out a 3x, x plus 3. We got to take out a -4, x plus 3. Then they both have x plus 3's. What's left? 3x minus 4. Zero product property again. Recurring theme here. X equals -3 and x equals 4/3. So this quadratic could be factored. And we got all three of the complex solutions we were looking for in this cubic using a GCF and a basic factoring method for quadratics. So we don't always have to go to the quadratic formula, but when in doubt, we can. 6, same idea. You're going to look at this and you're going to say, wait, if I take out an x right from the get-go, I'll just be left with a quadratic, which I know how to solve. So if we take out an x, we have two things being multiplied together equals 0. So let's not forget that x equals 0 is a solution from this GCF, okay, often forgotten. So there's one answer. Now we have to solve that quadratic. Let's do it by split the middle again, because we have an a value greater than 1, that 5. So a times c is 15. What multiplies to +15 adds to -8? Looks like -5, -3. So we will split accordingly. And recall that how you split the middle, or the order of the split, I should say, does not matter. So if we did -3x and -5x, we should still reach the same conclusion, or same solutions. Let's make our group. So I'm going to take out a 5x from the first group. We'll get x minus 1. -3 from the second group. Now they both have x minus 1. 5x minus 3 is left. So we've taken this quadratic and reformatted it as a product of two linear binomial terms equaling 0. We'll set each one equal to 0. We'll solve, and we'll get our remaining two solutions, x equals 1 and x equals 3/5. So if you forgot to set this GCF initially equal to 0 to solve that, you would still reach only two solutions. And what should go off in your mind, or the alarm that should go off, is that, wait a minute, I have a cubic, I'm missing a solution. So where do I get that final third solution? Again, I can't say enough how often it's forgotten that the GCF, if it contains a variable, will be responsible for some of the solutions, at least one. So don't forget about that piece. And if you happen to come across 2 and you know you need a third, check to see if that's what you forgot. The last 3 are going to be scenarios where factoring methods aren't going to apply. So we've seen some difference of cubes, factoring by grouping, GCF, factoring quadratics. We're using all of that to solve polynomials. But what if we can't factor? We have to use our rational root theorem. So we have to generate potential zeros. So remember, our p's come from our constant term, and our q's come from our leading coefficient. So p's are all the factors of that constant, so plus or minus 1, plus or minus 3. The q's are all the factors of the leading coefficient, which are the same in this case. So my potential rational zeros are plus or minus 1, plus or minus 1/3, plus or minus 3. So I only have 6 potential zeros. I'm going to evaluate the polynomial that I'm trying to solve at these potential rational zeros. Now, so using a calculator, we could say, well, what's f of 1? What's f of negative 1? What's f of 1/3? What's f of negative 1/3? What's f of 3? What's f of negative 3? Now, how many we have to check? We really only have to identify 1 0 out of this list. Because if I take 1 0, I can then use that 0 to reduce this cubic to a quadratic. But in the event that it's higher than a cubic, whatever the degree of the polynomial is, so let's say it's degree n, you want to find n minus 2 zeros from your list. If you can't find n minus 2 zeros from the list, there's a chance, or there's probably a really good chance, that another method could have been used. Maybe there was a factoring method that could have been used to find the additional zeros you're looking for. But if you're convinced that there's no factoring method to be used to solve the polynomial, whatever the degree is, subtract 2, that's the number of zeros you're looking for from your list. So, degree 3, 3 minus 2 is 1. So we're looking for 1 from our list of 6 numbers. So the first one we'll identify is negative 1. Okay, so upon evaluation, this is the first one that's going to give us a remainder of 0. That's what we're looking for, by the way. So when we plug in our list of possible rational zeros, we want remainder of 0. So we're going to use that remainder theorem we discussed. Once we've identified that, we're going to say x equals negative 1 is a solution. Okay, we already found the first one by checking our list. From there, if x minus 1 is a solution, then x plus 1 is a factor. So think of reverse engineering the factor or the polynomial expression that gave you that solution. So we're just moving that negative 1 to the other side of the equal sign. That's where that x plus 1 comes from. Once we've identified a factor, and we know it's a factor because the evaluation of its solution was 0. The remainder was 0, which is our factor theorem. So now that we have a factor, we're going to use long division to take the polynomial we started with and reduce it down to a quadratic. Or I should say, we'll reduce it to a polynomial 1 degree less than we started, assuming that my factor is of degree 1. If I generated a factor that was of higher degree, then it would reduce it even further. But carrying out the long division, Now, here's the thing. If we're dividing the polynomial by something that we have deemed as a factor, then the remainder better be 0. If the remainder is not 0, then either your factor is incorrect or you identified the wrong 0 from your list. Now, here's our quotient. We can take that quadratic and solve that to find our remaining two zeros. In this problem, this quadratic can be factored. Okay, so I'm going to do that. If you didn't recognize that it's factorable, then you can just use quadratic formula. So let's do the split the middle. So 3 times 3 is 9. What multiplies to 9 adds to 10. It would be 9 and 1. So 3x squared plus 9x plus x. Again, these are equivalent. We're just splitting the middle to identify a grouping. 3x from the first group. We're going to get x plus 3. We're going to take out a 1 from the second group because that second group's already what we want. X plus 3, 3x plus 1. X equals negative 3. X equals negative 1/3 when I solve those linear binomials. By setting each one of these equal to 0, I found all 3 of my solutions. 2 of them came from solving the quadratic. 1 of them came from the potential zeros list. And there is how we use rational root theorem in the event our original polynomial could not have been factored. Let's take a look at 8. Doesn't look like this thing could be factored. I don't see a grouping. There's no sum or difference of cubes. Doesn't look like there's definitely no GCF involved. So we're going to jump over to our rational root theorem. Let's generate our list. So the p's are going to come from the constant term. We're going to have plus or minus 1, plus or minus 5, plus or minus 7, plus or minus 35. I think that's it. And then for q, we're going to have plus or minus 1. So when the q is just plus or minus 1, then your p over q's ends up being just your p list, because taking all the p's, dividing it by all the q's would just be dividing it by 1. Upon checking this list, so we're going to evaluate our function at the 8 numbers. We don't have to do all 8. As soon as we find the first one that produces a 0 output, that would indicate that it is a 0, because the remainder would be 0 upon evaluation, or it equals 0. So when you evaluate that number, you get 0, so it's a 0. The first time that happens is when we evaluate at 5, so maybe the third or fourth number you check. Once we've identified that, let's write down our first solution. We know we're looking for 3. X equals 5 is a solution. We'll box that off. We're going to generate a factor from that. So if x equals 5, solution, x minus 5 is a factor. We're going to use that in long division to reduce this cubic to a quadratic. Let's carry out the long division. And by the way, when you're doing the long division, don't forget to look for placeholders if necessary. So far, we haven't seen any. We're going to get x squared, and then x squared minus 5x, or sorry, x cubed minus 5x squared, minus 2x, bring down to 17, change these signs. Divide. Get 0. That's what we want. That's a good thing. If we don't get 0, either our division was wrong, we screwed up in the long division, the factor that we generated was wrong, or the 0 that we checked was wrong. So if you're not getting 0, something's going wrong, identify what happened. Now, once I've carried out the division, my quotient is a quadratic that I'm going to solve. I cannot factor this one, so let's use another method. Let's use completing the square for the fun of it. The reason I'm going to do completing the square is I already have an a value equal to 1. My b term's even, if you remember that. So this is a good refresher and a good opportunity to use this. So completing the square, constants on one side, variables on the other. So I'm going to move that 7 over. Once I have that established, we're going to add b over 2 squared. So negative 2 divided by 1, or sorry, negative 2 divided by 2 is negative 1. Square it, you get 1. So we're going to add 1 to both sides. Okay, that's our completing the square part. Now, if you recall, what we've generated over here is something that is factorable. And if you factor that, you're going to get x minus 1 times x minus 1. X minus 1 times x minus 1 can be written as x minus 1 squared. Take the square root of both sides, because now it's just a matter of solving for x. Remember, when you take the square root of both sides, don't forget the plus or minus. We're going to add 1, remove the negative to identify the imaginary solution, aim to simplify the square root of 6 if possible. We can't. Here are two solutions that we found. In this case, I used completing the square. Again, quadratic formula is acceptable. We were looking for 3 complex solutions from the cubic. We found all 3. We are done. And then last problem for the video. Where is it? All right, here we are. Last problem. Can't factor, no GCF, no grouping, no sum or difference of cubes. So let's jump over to rational root theorem. Your p's, plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 4, plus or minus 6, plus or minus 12. Again, those are the factors of the constant term 12. And then q's are the leading coefficients, so plus or minus 1, plus or minus 3. So our list of potential zeros to get us started is going to be plus or minus, it's going to be the list of p's because I'm dividing it by 1, and then the list of p's all divided by 3. So let's list all the p's divided by 1. So I'm just going to rewrite that. And then all of the p's divided by 3 will get us the remaining parts of the list. So 1/3 plus or minus 2/3. 3 over 3 is 1, so we already have that, so I don't have to list it again. 4 over 3, we don't have 4/3. 6 over 3 is 2, we already have that. And then 12 over 3 is 4, we already have that accounted for. So here's our full list. So how many zeros do we have there? We have 18 possibilities to check. But again, we only need to identify whatever the degree of the polynomial is minus 2. So if it's degree 3, I only have to find 1. The first time you're going to find one is either, if this is your list, it's either going to be the 5th or the 6th number, because f of 3 equals 0, indicating that 3 is a 0. So if you evaluate a function at a number and the output is 0, you have identified a 0. So we're going to write down our first solution, x equals 3. From this, we generate the factor, which is x minus 3. Now let's carry out the division. Good, we got 0. So that means that 3, everything checked out. So 3 is definitely a solution. X minus 3 is definitely the factor. And my math up top, the quotient that I got, all this division worked out because I got 0. If I didn't, again, go back and check where you could have gone wrong. But you want 0 because if x minus 3 is a factor, then it should be evenly divisible by, or the polynomial should be evenly divisible by that linear binomial. So all that's left to do to find the remaining 2 complex solutions is solve this quadratic. We can't factor this thing. I don't want you to do completing the square because of that odd a term, because I'm going to have to divide both sides by 3, because remember, completing square, we want an a value of 1. So let's just jump right to quadratic formula. When in doubt, we can use it. So x equals negative b, so it's going to be positive 10 plus or minus b squared minus 4 times a times c all over 2 times a. X equals 10 plus or minus square root. We're going to have 4 times 3 is 12, times 4 is 48. So 100 minus 48 is 52 over 6. Square root of 52 can be simplified. Break this down into, actually, 4 and 13 gets me 52. So let's do that. So 4 times 13. So this is square root of 4, square root of 13. You can do your factor tree too, 2 root 13. Okay, so we're going to replace that. We're going to say 10 plus or minus 2 square root of 13 over 6. Last step. 10, 2, and 6 are all even numbers, can be reduced by a factor of 2. So 5 plus or minus 13 over 3. Again, there's two solutions here because of the plus minus. I found my first solution from the list. Obviously, I'm not going to be able to, so I'll just add that in. So x equals this and x equals 3, and there are my three solutions. This isn't in the list, so that's why we have to do this extra work, and we have to know how to be able to do it, because we have seen that there are solutions to these polynomials that are not in the list. Those are just potential rational solutions. We can see that there are irrational solutions. There are imaginary solutions. So using the division technique and being able to solve a quadratic with the methods we've discussed in previous units is going to come into play when solving polynomials that are not factorable, or we can't get all the solutions from the generated list of p over q's. So there's a video of multiple examples, multiple solution methods, and I hope that helps in your practice.